Hello everyone. In this mini lecture, I'm going to talk about experiment carbon steel. Here are the major objectives of the carbon steel. You'll learn how to interpret the microstructure of carbon steel at various carbon content. You'll also learn a technique to estimate the carbon content of steel based on the microstructure. You'll learn toughness and how to use Sharpie impact test to measure it. You also learn the ductile to brittle transition temperature behavior and how the carbon content affect this behavior and other mechanical behavior of the material. Okay, carbon content is an iron-carbon binary alloy with carbon content up to 2.1%. It is possibly the most important category of steel. They are typically categorized according to the carbon content as follows. For carbon content less than 0.25%, we usually call this type of steel as a low carbon steel. Within the range from 0.25 to 0.6%, it is a medium carbon steel. For the range between 0.6 to 1.25% or higher, we usually call that steel as a high carbon steel. Typically, increasing carbon content would increase the hardness and the strength of steel, but it also will reduce the ductility or increase the brittleness of the material. So in this experiment, we are going to focus on how this carbon content changes the mechanical property and the microstructure of the steel. Okay, let's first look at the microstructure of carbon steel. In this experiment, we are going to examine the microstructure of steel at different carbon content and interpret it using the phase diagram. So here is the phase diagram of the carbon steel, and because our carbon content is typically low, we're only focused on this region of the carbon content of the phase diagram. So in order to compare different carbon content, we typically will raise up the temperature to very high and cool down at a very slow rate so that it's easy for us to compare and interpret the microstructure of steel using the phase diagram. So the typical formation of the microstructure at a very slow cooling rate will be shown like this. Okay, so at the beginning, for the steel, we heat up at a very high temperature, mostly within the range that all the steel material get austenized, which all the material are the gamma phase. So once we start cooling the material at a very slow rate, and the material will slowly cool down and start from a phases that is the alpha phase in between the boundary of the gamma region. Okay, as the cooling continue, the region of alpha phase start to grow in a larger proportion until it's passing through the UTEC temperature, which is about 720 C, and the rest of the gamma region will turn into a eutectic region because we are using a very slow cooling rate. This region, the eutectic region, a pure light phase. So here I show an example of the microstructure we will see at this pretty much an example of this diagram. And the white region are the ferrite alpha phase. And then you can see they have some dark region with the laminar structure, which is the pure light. Okay, not only we can understand the microstructure using the phase diagram, we can also have a technique that uses the phase diagram to calculate the carbon content of steel. So the step will be like follows. First, we take a good image of the slow cool material, slow cool sample. Then we use the image software that's embedded in the microscope and select the high intensity range of the pixel. So the high intensity range of the pixel will highlight the region that is bright, which is associated with the area of alpha Ferrer phase. And the program, the software will automatically give us a value of percentage of alpha, percentage of area. The percentage area here is almost equivalent to the percentage of volume inside the material. Okay, so once we get that number, we can use the level rule. So as we explained, the level rule will show that the composition, for a certain composition, the weight percentage of alpha is equal to the length on the other side, that is the length of eutectic, divided by the entire length between these 2 points. So we get an equation looks like this. After some arrangement, we can get the composition equation looks like this. From here, the weight percentage of alpha is what we measure from the image analysis of the software from the microscope. Okay, and the CEU is a constant here, which is 0.76%, and C alpha is also a constant, which is 0.022%. Okay, so let's go through an example. Okay, here is the example image of the steel 1018. Okay, then I use the image software to measure the region of alpha phase, which is the region that highlight here. I get the percentage of area of highlight as 79%, which is the percentage area of alpha phase. So I just use this value in this equation here, and also I was going to plug in all these two constant into this equation. Then I get the composition at 0.177%. This is very close to the theoretical value of 1018 steel, which gave the carbon content at 0.18%. Okay, so that's a microstructural analysis of steel. You're going to look at 2 different steel with different carbon content. So then we're going to study a very interesting behavior. This interesting behavior is called ductile to brittle transition temperature. What happens is for some materials such as HCP and BCC metals will undergo a huge change in energy absorption because of when it at a very low temperature. Okay, this phenomenon is called ductile to brittle transition temperature. Usually described as this percentage of elongation versus temperature diagram. Once the temperature below decrease to a certain temperature, the ductility will significantly drop for quite amount. So it will drop from pretty good ductility at very decent amount of percentage elongation to almost no percentage of elongation when temperature drop. And this S curve at the deflection point of the SJ curve is called ductile to brittle transition temperature. Okay, so this behavior is related to the carbon content of steel, and we are going to study that. So to measure the ductility, we typically going to use impact tester, which measure toughness as the energy that's absorbed for sample to break. So this is the example. This image shows the impact tester at the Endeavor. The sample is located over here, and here is the big pendulum that's elevated at a very high position, which has the maximum potential energy. And once we start testing, we're going to open the safety lock and release the handle. The pendulum is going to cut through the Sharpie sample, and the dial will show the amount of energy the sample absorbed from the pendulum. Okay, in this experiment, we're going to have 2 groups of students, and each group will receive 1 type of steel. One group will receive low carbon steel as 1018. The other group will test a medium carbon steel that is 1045. Okay, then we are going to use this is the overview of the procedure of the experiment. Okay, so we are going to first normalize all the steel at 100 C, and then we will cool all the sample in air. Okay, so then we are going to perform the impact test at a different temperature to observe this ductile to brittle transition temperature behavior. So for 1018 sample, because it's pretty ductile material at room temperature, we need to lower down the temperature using dry ice. So you will listen the instruction of the TA how to control the temperature using dry ice, then test the sample at 5 different temperatures, at minus 60 C, minus 40 C, and minus 20 C, and 0 C, and 23 C. For the other group, they have 1045 steel, because this steel is more brittle at room temperature. So they're going to rise up the temperature somehow using the furnace. So they're going to test the sample at these 5 different temperature points, minus 20 C, 23 C, 75 C, 125 C, and 175 C. Okay, once you finish the impact test, and then you're going to polish the material and take the hardness measurement. Okay, so once you have this impact energy write down, you're going to compare how the temperature could affect impact energy. You could use the result to compare the reference from textbook. Here's the reference graph from one of our textbook. So as you can see, the x-axis is the temperature at the value of Celsius, and the y-axis is the impact energy. And this graph is for different carbon content. As you can see, for a very low carbon content, and you have a very sharp S-curve at a temperature pretty much at minus 75 C. Okay, once you increase the carbon content, this curve starts to flat down until it's become almost flat, and this brittle to ductile transition temperature behavior not become not so significant. So for 180, for 1018 steel, you're likely to see a curve that is between these two curves. That's the transition temperature is likely to be located as minus 40 C. Okay, for example, if you have steel as 1045, you're likely to see a curve pretty similar to something like this, and the transition temperature pretty much is located at 50 C. Okay, so that's pretty much for the main lecture. Good luck for your experiment.